Hello friends, welcome back to this series where we walk through the book on quantum mechanics by Steven Weinberg. This is lecture 26 and we shall be continuing with chapter 4 of the book, which is mainly about symmetries in quantum mechanics. Today, let's talk about internal symmetries. These are the symmetries of a system associated with transformations that do not involve in changing the space-time coordinates. And we are not talking about the intrinsic spin states of particles, which exist precisely to represent space-time transformations on the internal degrees of freedom of a particle. Rather, we are referring to the internal degrees of freedom that do not change under space-time transformations, such as Lorentz transformations, rotations, or space-time translations. These states are transformed only by the internal symmetries that we are about to introduce. Let's start with a nuclear system, the nucleons. It was recognized in the early days of quantum mechanics that the mass of the proton is very close to that of the neutron. The small difference in mass is attributed to the contribution from the electromagnetic interaction due to the proton's charge to the forces that bind the nucleons together. Most of the nucleon masses are due to the strong nuclear interaction. This similarity in masses is one indication that maybe the strong interaction treats the proton and the neutron on equal footings. The interchangeability of these two particles could be a symmetry of this interaction. A similar trend is observed in lighter nuclei, where the contribution from the electromagnetic interaction on their energies are minimal. Exchanging the proton and neutron numbers within a nucleus gives us another nucleus with similar energy. Recall the nuclear shell model based on the Nucleon Hamiltonian introduced in lecture 25. This Hamiltonian makes no distinction between protons and neutrons within the nucleus and is a fairly successful model in explaining the structure of the nucleus. This strengthens the hypothesis that the strong interaction makes no distinction between the two particles. Further evidence comes from observing nucleon-nucleon scatterings. The nuclear force between the proton and the neutron was studied by scattering a neutron off the proton in a hydrogen atom. And the nuclear force between protons was studied in proton-proton collisions in particle accelerators. More results about the strong interaction between the proton and the neutron come from the nuclear energy levels within the deuterium nucleus, also known as the deuteron. The results of all these experiments point towards a symmetry of the exchange between the proton and the neutron in the strong interaction. To be more precise, let's express this symmetry in terms of the symmetry of the strong Hamiltonian. The fundamental degrees of freedom of the proton and the neutron are themselves represented by operators known as quantum fields. All the observables of these two particles can be constructed out of these fields. The strong Hamiltonian is one such observable. The symmetry between the proton and the neutron is expressed as the symmetry of this Hamiltonian when the associated fields are exchanged. This is also known as the charge symmetry because a unit of electric charge is exchanged between the proton and the neutron. Let's treat these two fields as different components of a single field, capital Psi, forming a doublet. And the charge symmetry can then be expressed as the transformation of this doublet. We could thus view the proton and the neutron as different states of the same particle under strong interaction. Taking this idea further, one could imagine mixing these two particles in a more general way. An obvious choice would be applying a unitary matrix to this doublet. Notice that the charge symmetry can be expressed as the transformation of psi by the first of the Pauli matrices, which are generators of all the 2x2 unitary matrices connected to the identity matrix in a continuous way, but more about this later. There's a reason why we choose unitary transformations. These transformations will preserve the canonical commutation relations like those between position and momentum. The relevant commutation relations for the quantum fields psi will be between psi and psi dagger. Notice that we have also allowed the possibility of the anti-commutation relation, which is just the usual commutator but with an opposite relative sign. The reason for this is to account for the canonical commutation relations between fermions. But the details are not important here. We shall talk about them when we discuss quantum field theory later in this course. For now, you can think of psi and psi dagger as ladder operators, which creates or destroy particles, much like what you see for the harmonic oscillator. In a moment, we shall introduce a simple model that will make these ideas more concrete. Now let's transform psi by U. Here we use the Einstein's convention, where any repeated indices are summed over, to keep our notations concise. Notice that this preserves the commutation relations. This is an important feature, since if we are suggesting that psi and psi prime are equivalent in the eyes of the strong interaction, then they had better satisfy the same physical requirements like the canonical commutation relations. Now let's introduce the unitary operators in Hilbert space, which shall implement these matrix transformations. Note that U on the left-hand side is an operator in Hilbert space, while U on the right-hand side is an unitary matrix. Recall that the left-hand side is in the standard form of what we call the Heisenberg's picture of symmetry transformations way back in lecture 4. This transformation by U dagger also preserves the commutation relations of psi. Due to the unitarity of the operator U, thus the left-hand side of the transformation equation is consistent with the right-hand side. Let's introduce a change of notation here. We shall define the transformation with the indices of the matrix U transposed instead. This is to be consistent with our convention for operator transformations in lecture 24, where we discussed the Wigner-Eckert theorem for rotations. However, the details are not so important, since the transpose of a unitary matrix is still an unitary matrix. Let's look at the symmetry transformation of the Hamiltonian by the Hilbert space unitary operator. Using the unitarity of U, we have, and imposing the symmetry requirement. This is another way of expressing the symmetry of the Hamiltonian. To avoid any confusion between the Hilbert space operator U and the matrix U, let's add a hat to the Hilbert space operator. Here we can import what we know about rotational symmetry from lecture 19 and 23 and apply them to the current situation. The state space of a spin-half particle also forms a spin doublet, which can be expressed in the basis of spin up and spin down along the z-axis. Rotations are represented by the 2x2 unitary matrices generated by the Pauli matrices. The mathematics of these two symmetries are basically identical. The difference is only in the degrees of freedom that they are acting on. For the present case, we are only interested in the transformations of the internal states of a particle that are unaffected by space-time transformations, unlike the spin states. For our case, the transformations are known as isospin transformations. Notice that the generators are not only Hermitian, but traceless. Let's see what are the implications of this. Things are simpler if we just look at infinitesimal transformations. The finite transformations could just be composed out of these. If we look at this generator of U, notice that this is just the general expression for a 2x2 Hermitian matrix, which is also traceless if the epsilons are allowed to take any real values. This is consistent with the general result that any unitary matrix, which is continuously connected to the identity matrix, can be expressed as the exponential of I times a Hermitian matrix. We have derived this in Lecture 3. This result is valid for matrices of any dimensions. What we meant by being continuously connected to the identity matrix is that if we set A to be the zero matrix, U will be the identity matrix. Then by deforming A continuously from 0 to finite values, the entire family of unitary matrix would be generated. This family is thus continuously connected to the identity. But here, A needs only to be Hermitian and need not be traceless. We shall see what the traceless condition implies in general. Let's calculate the determinant of U. This is most easily done in the eigenbasis of A, where all the eigenvalues are real, since A is Hermitian. U itself will be a diagonal matrix in this basis. Thus the determinant would just be a bunch of phase factors multiplied together. Since we are treating the general case of arbitrary dimensions, there are as many phase factors as there are eigenvalues. Thus the exponent of the result would just be the sum of all the eigenvalues of A, which is its trace. From the condition of unitarity, the absolute value of the determinant of U must be equal to 1. One possible way of satisfying this condition is for the determinant itself to be equal to 1. Notice that this means the trace of A has to be equal to 0. Thus we see where the traceless condition for the generators of U comes from. It comes from requiring that the determinant of U be equal to 1. This is the general case of the family of n by n unitary matrices with determinant 1, also known as SUN, which we have discussed in Lecture 19 and 23. Note that for this general case, the dot product must be extended to more than 3 components. This corresponds to more than 3 generators, which are required to generate the entire family of unitary matrices. However, as mentioned earlier, in general, the determinant of an unitary matrix need not be equal to 1. Only the absolute value needs to be 1 by the unitary condition. So let's look at this more general case and see what it implies. It is not difficult to see that removing this one real constraint will give us an extra real degree of freedom in the form of an overall phase. Another way of looking at this is through the matrix A. Now, not only does A contains a traceless part, it also has a part that carries its trace, which is to say that A could be any Hermitian matrix. We call this overall phase the trivial part of U, since it is just a multiplication by an ordinary number and does not mix the different components of any column vector that it is acting on. The non-trivial part would then be our original SUN. We have simply chose to focus on the non-trivial part of the transformations, which are generated entirely out of traceless generators. Now let's go back to the example of 2x2 unitary matrices, or the SU2. As we shall see, even though we are talking about SU2, we need not restrict ourselves to the 2x2 matrix representation. If only we distill out the essential properties of these matrices and treat them as a symmetry group. For this, we turn to our results from lectures 3 and 4, which are all about Lie algebras and symmetries. It turns out that the essential features of a symmetry group is captured entirely by the algebra of its generators. Recall that this is the SU2 algebra, associated with the rotations of 3-component vectors in real space. The epsilon symbol is just a Levi-Civita symbol. The generators form an algebra when the commutator of any two generators can be expressed as a linear combinations of the same generators. The relation in the yellow box completely determines how two group elements will combine to give a third element, which is to say how the resulting transformation parameters depend on the two original set of parameters is entirely determined by the algebra. This composition rule basically defines a symmetry group. The SU2 algebra allows us to extend the representation of rotation or isospin beyond 2x2 matrices to n by n, as long as we replace this set of 3 generators to the corresponding n by n ones, which also satisfy the SU2 algebra. Note that this higher dimension representation will still have the same number of generators, since it is basically the same group. This will allow us to move beyond the isospin doublet to higher dimensional multiplets. Specifically, we will be looking for irreducible representations of SU2 in these multiplets. We have discussed the irreducible representations of symmetry groups extensively in lecture 23. Roughly speaking, an irreducible representation consists of vectors that are transformed by the symmetry into vectors that remain within the same state space which defines the representation. Furthermore, we cannot find a smaller state space within this representation that are invariant under the symmetry transformations. This means any vector within such a subspace can be brought out of it by some transformation of the symmetry. As we have seen from the isospin doublet, each component within the doublet is actually a unique particle. It's just that if SU2 is the symmetry of the strong interaction, then each component is treated by the interaction as different states of the same particle, with similar reaction rates under the strong interaction. But these are actually different particles with different charges and masses, since they participate in other interactions apart from the strong interaction. This also implies that we can predict the existence of new particles that are missing within a suspected multiplet of the symmetry. Let's go back to the isospin doublet and look at the associated particle states. To do this, we define a vacuum state that is completely symmetric, such that the action of any SU2 generator brings it to zero. This implies that any transformation from the SU2 group will leave our vacuum unchanged. We have written this with a dagger purely out of convention. Recall that each component of our doublet is an operator associated with the quantum field of a particle. In our case, these are the proton and neutron. Applying these operators to the vacuum will give us the corresponding particle states. We have used a similar construction in lecture 24, when we discussed the Wigner-Eckert theorem. Such a formalism can be applied to a higher dimension multiplet. There's actually a lot more particle states than we led you to believe here. This is more like a schematic representation that captures the essential transformation properties of the states. The only quantum number we are interested in is the group index I. All the rest, like position, momentum, or angular momentum of a particle, are hidden. Now let's figure out how these states transform under the generators of the symmetry. We can use the result from earlier on the transformation of fields. Let's expand both sides in a power series in the parameters epsilons. Comparing the coefficients of the epsilons. We have this result. Now let's apply both sides of this operator equation to the vacuum state. Expanding out the left-hand side of this equation, and using the symmetry of the vacuum state above. We can now identify the particle states in the multiplet on both sides. This is how the generator operators act on the basis states within a symmetry multiplet. They are simply multiplied by the matrix representation of the corresponding generator. We can apply this result to any state in the multiplet. Here we see how the amplitudes of an arbitrary state in the multiplet transform under the action of a symmetry generator. Substitute in the transform amplitude. And we have the result we are after. For an explicit example of its application, let's look at the isospin doublet. The amplitudes alphas now form a two-component column. The proton state then corresponds to the column with the upper entry, and the neutron state the lower entry. With these information, we can easily calculate the action of a generator on a proton state by substituting the proton column into our formula. Let's look at the action of the third generator. For SU2 symmetry, the matrix T3 is just half times the third component of the Pauli matrices. This just gives half times the proton state. Similarly, the neutron state is an eigenstate of T3 with eigenvalue minus half. Now we construct the ladder operators for isospin. This is the direct analog of the ladder operators for angular momentum introduced in lecture 20. The raising operator acting on the proton state gives. Substituting in the matrices for T1 and T2. Which is 0, as it should be, since the proton state is the highest weight state within the isospin doublet. Similarly, we can look at the action of the lowering operator on the neutron state, which is 0, as expected, since the neutron state is the lowest weight state of the isospin doublet. Raising the neutron state gives us the proton state. And lowering the proton state gives us back the neutron. Here's a quick summary of all the results on the isospin doublet. The basis states of the doublet are eigenstates of the third component of isospin, while the ladder operators transform between basis states. These are the exact replica of our results from the spin-half doublet of angular momentum, which is to be expected since they are both representations of SU2. As we have just seen, we could effectively replace the states in an isospin doublet with columns of ordinary numbers, and the symmetry generators by matrices which act on these columns. It is quite obvious that the electric charge could also be expressed as a diagonal matrix in this basis. The upper diagonal is the charge of the proton, while the lower diagonal the neutron. We can write this as the sum of two matrices. Thus we see that there is a direct relation between T3 and the electric charge. They are not independent. This relation holds for the single nucleon isospin doublet. Now let's extend this result to n nucleons. This is just the sum of all their individual charges. For each Q, we can use the single nucleon result above. Summing all the factors of half, we have n over 2. The sum of all the individual isospins gives the total isospin, which we still use the notation T3 hat. This is how the total charge of an arbitrary number of nucleons relates to their total isospin. We denote n over 2 by the mass number operator divided by 2. Recall that the mass number is simply the number of nucleons. Thus we now have a general formula which relates the charge of a nuclear system to its mass number and isospin T3. This formula holds for many nuclei and their isotopes. Note that we have assumed that the number of nucleons A is also conserved by the strong interaction. Since both Q and T3 are conserved quantities. Now let's look at the general structure of an isospin multiplet. This is of course just the SU2 multiplet we have studied in lecture 20, which is based on the SU2 algebra of the generators. There is a one-to-one correspondence between the angular momentum multiplets from lecture 20 and the isospin multiplets. To make a distinction between these two cases, let's denote the square magnitude of isospin by T. As derived in Lecture 20 from the commutation relations, t can take all the positive integer and half-integer values, while the third component of isospin ranges from -t to t at integer intervals, adding up to 2t plus 1 states within a multiplet labeled by t. Apart from the isospin quantum numbers, each state would probably contain some other quantum numbers, such as the nucleon number A, spin J, and all the other quantities that are invariant under isospin transformations. For these, we shall not display them explicitly, since we would mostly be looking at symmetry transformations. For a given t, the formula above would then fix the charges of all the particles in the multiplet. As an example, let's look for isospin multiplets among the nuclei. Here we have a triplet of nuclei with nucleon number 12 and spin 1. And of course, an isospin triplet corresponds to t equals 1. The asterisk on carbon 12 indicates that this is an excited state. But how do we know that this is an isospin triplet in the first place? Apart from the fact that these nuclei have the same number of nucleons and spin, we can also gain some information from their charges. Using the formula for charges within a multiplet, we can work backwards to figure out their isospin. These are the values that correspond to the triplet t equals 1. For the next example, let's go beyond the nuclei. The pions, which are spin-zero particles with masses that are an order of magnitude smaller than the nucleons. The charged pions, both positive and negative, were discovered in 1947, while the neutral pions later in 1950. This neutral particle could already be anticipated from its charged counterparts, just from isospin symmetry. Typically, pions are produced in nucleon-nucleon scattering. It was thought that the nucleon number was conserved by any process in nature, not just for strong interaction. From this interaction, the pion must be assigned a nucleon number of 0. Substitute this into our charge formula, we have the existence of charged pions implies that they must belong to an isospin multiplet, which contains the values +1 and -1 for T3. This means the multiplet must at least contain an additional neutral particle with T3 equals 0, and T greater or equals to 1. Turns out that T equals 1, and the 3 pions form an SU2 triplet. So the SU2 symmetry of the strong interaction allows us to predict the existence of the neutral pion. This really is the story of much of modern particle physics, where physicists predict new particles from the symmetries of nature. For our next example beyond the nuclei, let's look at the delta particles. These are a set of 4 particles that are slightly heavier than the nucleons, but are in the same order of magnitude. So we might expect their nucleon number to be also 1. They all have spins of 3 halves and form an SU2 multiplet with T equals 3 halves. Assuming that A equals 1, and again using the charge formula, we can figure out the value of T3 for each member. This shows that T is equal to 3 halves. But how do we know A is really equal to 1? By observing how the delta particles decay. They decay into a pion and a nucleon. Since A equals 0 for the pions, this implies A equals 1 for the deltas, because the strong interaction preserves nucleon number, and we know that this is a strong process by the fast decay rate. Let's quickly verify the values for T3 in details, using the charge formula with A equals 1. Now let's look at this strong process and work out the consequences of isospin symmetry on the decay rates. The decay rate of this process is proportional to the square magnitude of the amplitude between the pion-nucleon product state and the delta state. The constant of proportionality is some positive quantity that is not dependent on isospin. To see where this expression came from, see lecture 15 when we talk about selection rules in atomic transitions. But we can see why this expression is true. Since the isospin is conserved by the strong interaction, the time evolution generated by it on the initial product state must not change its identity as an eigenstate of isospin. So we can only find a system in a final state that has a non-zero overlap with the initial eigenstate. This is captured by the prefactor. The numbers m, m prime, and m double prime are the values for T3 of the states in their respective isospin multiplets. If this amplitude looks familiar, it's because it's one of those Clebsch-Gordon coefficients we have seen in lecture 21. Though back then we were talking about angular momentum states, now we are dealing with isospin. So even though we are using the symbol J here, this refers to isospin. For this amplitude to be non-zero, J must be one of the values between the magnitude of the difference and sum of J prime and J double prime. At the same time, M must be equal to the sum of M prime and M double prime. These are the selection rules. We have calculated some examples of these coefficients in lecture 21. You can find a table of these numbers in most quantum mechanics textbooks on Wikipedia. Let's first look at the decay of delta plus plus into pi plus and a proton. Notice that the selection rules are satisfied. Actually, both states in the amplitude are equal. They both are the highest weight state in the multiplet, with T equals 3/2. Assuming that both states are normalized, the square magnitude of their bracket must be equal to 1. And the decay rate is just the constant of proportionality, which is independent of isospin. We denote this as gamma 0. Let's examine the symmetric properties of the transition amplitudes. Using the unitarity of symmetry transformations, we have set U to be an isospin transformation, specifically 180 degrees rotation about the second axis. The reason we choose such a transformation is because This changes the values of the isospin T3. This allows us to relate the original transition amplitude to those of transitions between different members of the same two multiplets. Let's see this transformation in details. What is the value of T3 for the state U on Jm? T3 is flipped around by the transformation. Minus T3 acting on the state Jm just gives minus m. Thus U on Jm is equal to J minus m. So the transformation above flips the value of T3 for the state. But of course, the transformed state would still be in the same isospin multiplet. Similarly for a product state, we have going back to the earlier transition amplitude and applying our results. And here we have the relation between the amplitudes mentioned earlier. Let's apply this to the decay of delta particles. First notice that the particle that is in the inverted position to delta plus plus within the delta multiplet is delta minus. Similarly, pi minus is inverse to pi plus in the pi multiplet, while the neutron is inverse to the proton. So this amplitude is equal to, by the relation below. Thus the decay rate of delta plus plus in the pi plus and the proton is equal to the rate of delta minus decaying into pi minus and a neutron. This is the consequence of the isospin symmetry of the strong interaction. We can do the same for the decay of delta plus into pi plus and a neutron. This is equal to the rate of the inverted process. But what is this rate? This should be a fraction of gamma 0, and we get this fraction from the Clebsch-Gordan coefficients, as we shall do later. The reason is due to the fact that the process above occurs at the highest rate for these multiplets, since the two states in the bracket are basically the same highest weight state. Thus the inner product is equal to 1, and the inner product between any two normalized states must necessarily be less than or equal to 1. Another way for delta plus to decay is into a neutral pion and a proton. This is equal to the rate of the inverted process. Note that we are using the word inverted quite loosely, and this is in no way related to the inversions or parity transformations, which we shall discuss later in this chapter. What we have here is really the 180 degrees isospin rotation. Now let's calculate the rate for this second set of processes. Let's work out the Clebsch-Gordan coefficient. J equals 3 halves and M equals half. J prime equals 1 and M prime equals 1. J double prime equals half and M double prime equals minus half. Let's check the table for the Clebsch-Gordan coefficient that corresponds to these figures. This is the relevant row, and the value for our coefficient. You can find this table in Weinberg's book. Also check out lecture 21 to see how to calculate them. So the corresponding amplitude is equal to 1 over the square root of 3. This gives an absolute square of 1/3. And this is our decay rate. Now let's look at the third process. Let's check the table for these figures. So these are the consequences of the isospin symmetry of the strong interaction on the decay of delta particles. They agree with what we observed in experiments to a good approximation. Our next example concerns a set of particles known as the Hyperons. These are spin-half particles with masses that are of the same order of magnitude as the nucleons, but heavier. Similar to the deltas, these are unstable particles. Looking at their masses, the particle lambda 0 stood by itself, having a smaller mass, while the 3 sigma particles are heavier and similar in mass. So it is reasonable to consider lambda as an isospin singlet and the sigmas as triplets. The reason why these particles are considered together is that they decay in similar ways. These decays occur through the weak interaction. This is a much weaker nuclear force compared with the strong interaction. The typical lifetimes of these particles are roughly on the order of 10 to the power of minus 10 seconds. Compare this with the typical time scale of the strong process, which is 10 to the power of minus 25 seconds. This means a weak process occurs much more slowly than a strong process, which makes them easier to distinguish. As mentioned earlier, we have assumed the Nucleon number to be conserved in any process, including weak processes. This allows us to deduce the value of A for the Hyperons. They have a Nucleon number of 1. Since both the delta particles and the Hyperons have Nucleon numbers that are equal to 1, but are nevertheless not Nucleons, let's generalize A to a broader quantum number we call B to encompass all these particles. B is called the Baryon number. An additional point we need to emphasize is that, for their antiparticles, we need to include an extra minus sign. An antiparticle is identical in every way to its particle counterpart, except for this minus sign. Our charge formula should also be modified. Does this formula still hold in light of all these new particles? Let's check. Starting with lambda 0. With B equals 1 and T3 equals 0, this suggests a charge of half, which is obviously wrong since lambda is a neutral particle. So we should correct this by subtracting a half unit of charge. This can be written as this is equivalent to modifying the Baryon number by a new quantum number, which is called Strangeness. The previous examples where the old charge formula holds just correspond to cases where Strangeness is 0. Lambda 0 has Strangeness equals to minus 1. What about the sigmas? Setting B equals 1, their charges should be equal to. We can use this to work out the value of S for the sigmas. First notice that the values of T3 and Q are identical for each sigma particle. This implies S equals -1 for the sigmas. Therefore, the hyperons have strangeness equals -1. As we have said, for all our previous examples, S is equal to 0. Our new charge formula holds for all these cases, and we shall assume this to be true where the strong interaction is concerned. One thing to notice from the weak decays of the hyperons is that strangeness is not conserved by the weak interaction. On the other hand, it is conserved by the strong interaction, as we can see from the strong decay of the delta particles. Furthermore, as we can see in all our examples, the value of strangeness is the same for all members of an isospin multiplet. This implies that strangeness is also invariant under isospin transformations. The same goes for the Baryon number B. Let's look at another example with non-zero strangeness. In nucleon-nucleon collisions, in which the hyperons are produced, together with them came particles known as Kaons, which have spin 0. This is another strong process. The Kaons themselves also belong to some isospin multiplet, a doublet to be precise. In fact, any particle that participates in the strong interaction belongs to some isospin multiplet, or else they won't transform in a well-defined way under isospin transformations. The Kaons have masses that are lighter than the nucleons. Assuming that the strong interaction conserves strangeness, the Kaons must then have a strangeness of +1. Baryon number conservation implies that the Kaons must have a Baryon number of 0. Again, let's verify that the Kaons satisfy the charge formula. Substituting in the value for B plus S, Q is given by T3 is and Q which agrees with the charge formula. Let's look at one more example, the Xi particles, which form another isospin doublet. These are spin-half particles that are heavier than the nucleons, but again within the same order of magnitude. So we posit its Baryon number to be 1. Setting S equals -2 will make the charge formula works for this doublet. Looking at T3 and Q for the doublet, and substituting in this value for B plus S into the charge formula, we find again that this formula does indeed reproduce the charges in an isospin multiplet. Notice that only the sum of B and S enters into the charge formula, which is to be expected, since both these numbers are shared by all members of a multiplet. This fact will be important in a minute. Let's examine the symmetries of the strong interaction in details. The first is the isospin transformation. The second is charge conservation. This second symmetry is exact, as far as we can gather from all our observations, while the isospin symmetry is an approximate symmetry since the masses of all the particles within its multiplets are not exactly equal. Alpha is a real parameter associated with the transformation generated by Q. These symmetries imply that their generators commute with the strong Hamiltonian. Now we define what is known as the hypercharge. This is the sum of the Baryon number and strangeness. Rearranging the charge formula gives since both Q and T3 commute with H, this implies that so do the hypercharge. The hypercharge is thus conserved by the strong interaction. As we've mentioned earlier, the particles in the same isospin multiplet share the same Baryon number and strangeness, and so the hypercharge too. This implies that the hypercharge commutes with all the isospin generators. This results from the fact that the generators can only move states around within the multiplet and never out of it. Let's show this explicitly. Psi is any state within an isospin multiplet and has a hypercharge of Y. The hypercharge of the state from an arbitrary isospin transformation on psi is also Y. Since this state must remain within the multiplet, and all states within the multiplet must share the same hypercharge, this value Y can be replaced by the action of the operator Y hat on psi. This equation implies that the arbitrary isospin transformation commutes with Y, which in turn implies that the hypercharge commutes with all the isospin generators. Note that Y commuting with H means that the strong interaction is also symmetric under the transformations generated by Y. But this symmetry is not independent of that generated by Q according to the charge formula. Thus we only need the isospin symmetry and either one of these. We shall choose the hypercharge symmetry since it has a simpler commutation relation with the isospin generators. Notice that Q only commutes with T3 but not with T1 and T2 by the charge formula. This is also apparent by the fact that the particles in an isospin multiplet all have different charges. At this point, we simply have two sets of independent symmetries which commute with each other. Now we might make another hypothesis. Could these generators be part of a larger symmetry group? Perhaps some SUN with n larger than 2. Could there be a higher symmetry within the strong interaction? Let's recall some of the important properties of the SUN matrices, which this symmetry group is based on. All n by n unitary matrices that are continuously connected to the identity can be expressed in such an exponential form, where A is a Hermitian matrix. In addition, A being traceless will give us SUN matrices with determinant equals 1, as we have shown earlier. With these conditions, any matrix A can be expressed in the basis of Hermitian traceless matrices in terms of a set of real coefficients. These matrices lambdas are then the generators of the SUN matrices. Let's count the number of real parameters needed to describe A. We do this by considering these two constraints. We have already done this exercise in lecture 23, but it's worthwhile going through again. The Hermitian condition means that the matrix elements Aij obey these equations. The first equation concerns the off-diagonal elements, This implies that there are n times n-1 over 2 number of independent complex equations, multiplied by 2 to give the number of real equations. The second equation means that there are n number of real diagonal elements. The sum of all these gives n times n plus 1 real constraints. The number of real parameters that describe the matrix A is 2 times n squared minus the number of constraints. Finally, for the traceless condition, this is a real equation since all the diagonal elements of A are real. So we subtract the number of parameters by 1. Thus the group of SUN matrices has n squared minus 1 generators, one generator for each parameter. Now let's look at one example of an irreducible representation of SUN that most readily suggests itself. Consider any traceless Hermitian matrix B expressed in the basis of the generator's lambdas. The betas here are real components. Assume that B undergoes SUN transformations in the following way, which is the usual way observables are transformed in the Heisenberg's picture. Notice that the transformed matrix B' is still Hermitian and traceless, since the transformation of this form on the left-hand side preserves these two qualities, as you can easily check. Thus B' can also be expressed in the basis of lambdas. Furthermore, we know that this is an irreducible representation because any traceless Hermitian matrix can be transformed into any other traceless Hermitian matrix by some SUN transformation. First, here's the proof that such transformations preserves the hermicity and tracelessness of the matrix. It is obvious that B' is Hermitian as long as B is Hermitian. Next, we show the tracelessness. To show that this representation is indeed irreducible, we must go a step further. From this equation, the transformed parameters beta prime is related to the initial parameter beta by such an equation. Beta prime can then take any set of real values for fixed beta by an appropriate choice of alpha, because there are just a necessary number of free parameters to match the number of equations. This shows that, starting with any traceless Hermitian matrix, we can turn it into any other traceless Hermitian matrix by a SUN transformation. B is indeed an irreducible representation of SUN. This representation is immediately available to us with any SUN. The most straightforward way we could extend the isospin symmetry of the strong interaction is to just promote SU2 to SU3. From our general results from SUN, the SU3 group would have 8 generators. The irreducible representation B then corresponds to an 8-particle multiplet. Let's look for such a multiplet among our previous examples. Each bracket contains a SU2 multiplet. Let's look at those with the same spin, for example spin half, such that it is possible for all of them to belong to an SU3 multiplet, which is a symmetry that is independent of rotations. Notice that we have exactly 8 particles. These fit together in a very nice pattern. This is the 8-particle multiplet we are talking about, also known as an octet. Gell-Mann called this the eightfold way. The vertical axis is the hypercharge, and the horizontal axis the third component of isospin. Each row contains an SU2 multiplet. Although both the SU2 and SU3 symmetries of the strong interaction are approximate, the wider variance and masses within an SU3 multiplet means that it is less exact. Let's look at the smallest representation of the SU3 symmetry, or its fundamental representation, in the form of 3x3 matrices. But first, let's examine the SU2 in more details, since it is a subgroup of SU3, as we can see from how the SU2 multiplets are embedded within a SU3 multiplet. The smallest representation of SU2 is in the form of 2x2 matrices acting on a doublet. Our aim is to describe the zoo of particles which participate in the strong interaction in terms of a small number of fundamental particles that might fit into this smallest multiplet, which are the constituents of all the other particles. But the nucleon doublet would be too massive to be these constituent particles. For example, it is an order of magnitude larger than the pions. Instead, suppose these constituent particles form another doublet. Let's call them quarks. The up quark for the upper entry of the doublet and the down quark for the lower entry. Similar to the nucleon doublet, let's assume that these quarks have a strangeness of 0. The two basis states of the doublet are produced by applying the corresponding fields to the vacuum. In the notation of an isospin doublet, we have Let's try to construct the heavier nucleon doublet out of the quarks doublet. Putting two quarks together, from these basis states, we can construct two sets of states with isospins t equals 0 and t equals 1, each forming a SU2 multiplet. This is what we have worked out in lecture 21 from how angular momenta are added for quantum states. As you can see, two quarks could not form an isospin doublet. What about three quarks? Adding another isospin half quark to the previous two gives a t equals half and t equals 3 halves multiplet. And here we have a candidate for the nucleon doublet. The proton has a value of half for T3. This can be made up with 2 up quarks and 1 down quark. For the neutron with a value of minus half, this corresponds to 1 up quark and 2 down quarks. Let's figure out the charges of the quarks from the charges of the proton and neutron. This should work since there are two equations to solve for two unknowns. The sum of these two equations gives, which leads to eliminating Qu with the second equation. This implies that the down quark has a charge of minus 1/3 in units of the charge of the electron. And using the earlier relation between Qu and Qd, we have With these, let's calculate the hypercharge of the quarks using the charge formula for the isospin multiplets. Recall that the hypercharge holds for an entire isospin multiplet. Now we are ready to look at the SU3 representation of quarks, which is the broader symmetry that we are now assuming the strong interaction to possess. The smallest representation should contain 3 elements. For the third element, we add a new quark in addition to the up and down, and call this the strange quark, which carries all the strangeness of the SU3 multiplet. Remember that the up and down has s equals 0. Let's assign a strangeness of -1 to the strange quark. This extra quark could explain the mass variance between the SU2 multiplets within the SU3 multiplet if its mass is much different from the other 2 quarks. Let's assume that this is a heavier quark, which would explain why it was discovered after the other 2, because it takes more energy to produce and decays faster. The isospin generators for SU2 matrices are 2x2 matrices. What should they look like in the SU3 representation? To make a distinction between the 2 cases, let's denote the 2x2 isospin by little t. For the 3x3 case, a straightforward extension would look like this, which we denote by capital T. The isospin will act in the same way on the up and down quarks, but they will give 0 on the strange quark. This means an isospin transformation will leave it unchanged. This construction will automatically obey the traceless condition, as long as the 2x2 version is traceless. More importantly, the 3x3 isospin generators will also satisfy the SU2 algebra, as long as the 2x2 version do. Now we shall construct the hypercharge matrix. Recall that the up and down quarks have hypercharge of 1/3. The hypercharge of the strange quark is then fixed by the traceless condition, which is satisfied by all the generators of SU3. And the strange quark has a hypercharge of -2/3. These matrices obviously satisfy the commutation relation we have derived earlier. The hypercharge and the 3 components of isospin are among the 8 generators of SU3. Lambdas 1 to 3 are proportional to the isospin generators, the 8th to the hypercharge. Let's write the unitary operator by the usual convention in terms of the generators. The lambdas are the Pauli matrices for the SU2 and the Gell-Mann matrices for SU3. For completeness, here are the rest of the Gell-Mann matrices. Notice that the isospin generators and hypercharge do not mix the strange quark with the up and down quarks, but the rest of the generators do. It is important to note that there is nothing special about the Gell-Mann matrices. They merely provide a basis for expressing Hermitian traceless matrices in terms of the real components alphas. Now we look at a general scheme that will allow us to construct representations of composite particles out of the smallest representation, which contains the most elementary particles, like the quarks. Let's make an assumption that the relevant laws of nature possesses a SUN symmetry. The smallest representation would be n by n unitary matrices. Recall that any particle that participates in the interaction with this symmetry must be part of an irreducible representation of SUN. Thus, once we have the elementary particles, the symmetry of the group will tell us what are the possible composite particles and the multiplets to which they belong. These matrices act on columns of n components, each representing an elementary particle. This is how the particles transform under SUN. But how do the antiparticles transform? Simply take a Hermitian conjugate. Notice that nevertheless, U star remains an unitary matrix with determinant 1, much like U. Why does the Hermitian conjugate represent an antiparticle? Just look at the transformation generated by the hypercharge. Given that Y is a real matrix, U star just gets an extra minus sign. This just means an antiparticle has an opposite charge to its particle counterpart. The particle and antiparticle states of a given flavor, labeled by I, are produced by their field operators acting on the vacuum state. And the way these states transform under the SUN symmetry are thus determined entirely by how the fields transform. Out of these states, we can build the states of composite particles, which may be composed of several of these particles or antiparticles. We do this by taking the tensor products of these states and their superpositions. In general, states with n particles and m antiparticles look like this. The coefficients are objects with both upper and lower indices, known as tensors. This is the tensor representation we have introduced in Lecture 23, specifically for the rotation group. Here we shall develop a more general formalism. In order to produce the irreducible representations of SUN, these tensors must possess some definite properties, which we shall now get to. First of all, the upper and lower indices must be separately symmetric among themselves. The reason is that the lower indices contract with the particle states, and it shouldn't be important which order these states are arranged within the tensor products. The same applies to the upper indices with the antiparticle states. Let's see how this state of a composite particle transforms under SUN. This is quite straightforward. Just apply the transformation rules for the single particle states to each state in the products. We can express this transformation in terms of how the tensor coefficients transform, by comparing the expressions in the red boxes. First of all, change the prime indices to unprime indices and vice versa in the lower box. This allows us to compare the tensors as they are contracted with the same basis states. This is how the tensor coefficients transform under SUN. Let's replace all these U matrices by their transpose. This will allow us to switch around the indices of U. Finally, we have the transformation rule for the tensor coefficients. What we have done by taking the transpose is merely a change in convention to match those in Weinberg's book. Notice that the symmetry of the indices is preserved by this transformation. And this is achieved without any additional conditions on the matrix U. All that is required is that this is a linear transformation. Here's the second condition that these tensor coefficients have to satisfy. This is the traceless condition. Contracting any pair of upper and lower indices must give 0. And it doesn't matter which pair, due to the symmetry of the indices. This condition is also preserved by the transformation above. This is due to the unitarity of U. We can see this directly. Let's take a trace of the transformed tensor. Contract the first pair of indices. Again, it doesn't matter which pair. Now invoke the unitarity of U. This trace is equal to 0 due to the tracelessness of the original tensor. Thus both of these conditions satisfied by the tensor are preserved by the SUN transformations without any additional conditions on the matrix U. U just needs to be linear and unitary, which is exactly the definition of the SUN matrices. This is why the tensor coefficients defined this way are associated with irreducible representations of SUN. The special condition of determinant 1 is not important here, since this has to do with whether there is an overall phase attached to the unitary matrix, and such a phase has no role in mixing up the different components of the tensor, which is what the whole business of an irreducible representation is all about. There are no subset of components that are mixed only among themselves under SUN. In order for you to mix the tensor components in a disjointed manner, the way a reducible representation would, we would need to put extra constraints on U beyond the minimal conditions that it automatically satisfies. Such constraints would reduce the ability of U to mix up the tensor components. An example should clarify our point. Suppose U is instead an n plus 1 by n plus 1 unitary matrix, and all indices ran from 1 to n plus 1. Let U be a representation of SUN instead of SUN plus 1. This means its generators must satisfy the SUN algebra, and there are altogether n squared minus 1 generators. These are additional constraints on U on top of its unitarity, such that U would reproduce the composition rules that characterize SUN. This is what we meant by a representation of a symmetry group in the general sense. These additional constraints are precisely what we have mentioned earlier that would impede the ability of U to mix up the tensor components. And so, this tensor representation would no longer be irreducible. One more example from the SU2 rotation group. Let's look at an angular momentum multiplet with quantum number J, which we know has 2J plus 1 basis states. This is an irreducible representation of rotation. Therefore the U's, which represent rotations within this multiplet, are 2J plus 1 by 2J plus 1 matrices. Suppose we have a different multiplet, labeled by J prime, which forms another basis. This is another irreducible representation of rotation, which cannot be connected to the first by any rotations. States in one representation can never be rotated into states in the other. One could now imagine combining these two bases to create a larger state space, which might also contain states that are superpositions of states from both bases. The representation of rotations in this combined state space is therefore reducible. Whereas the general unitary matrices U in this space, not just those that represent rotations, are sort of irreducible. They only need to satisfy unitarity, without any additional constraints. The constraints that picked out the matrices UR from the entire set of U is precisely the SU2 algebra that has to be satisfied by its generators. Let's get back to our discussion on the tensor representation of SUN in terms of tensors that are both symmetric and traceless. Now we shall see how this works for SU2 transformations. All the indices take two possible values. Just to remind you, the lower indices of the tensor transform by the matrix U, while the upper indices by its complex conjugate. We claim that any upper index object can be constructed from a lower index one and vice versa. This means the lower index objects are the only independent components we need to consider. Let's show this. To make our point, we only need to deal with a tensor with just one lower index. This transforms by U. Let's define an upper index tensor by a contraction with the epsilon symbol, such that the epsilon is basically raising the index. Thus this object transforms by U star just like an upper indexed object. Here's the most straightforward way to define the transformation, by replacing the lower index psi by its transformation. Substituting in the expression above, we have another place where an epsilon symbol appears is in the determinant. Let's look at the determinant of U. The epsilon appears in the Leibniz formula for a determinant. The anti-symmetry of epsilon allows us to rewrite this expression. This just tells us that switching the free indices 1 and 2 gives a minus sign. So we have an anti-symmetric two-index object with indices taking two values and which has a magnitude of 1. This is just the epsilon symbol. Thus the determinant of 1 implies that the epsilon symbol is invariant under SU2. The same is true for U star, since this is just the complex conjugate of the upper equation. Let's use the identity below for this epsilon. Then using the unitarity of U, by definition, this is just psi with an upper index of I prime. Thus we have proven our claim that a lower index can be converted to an upper index by an epsilon symbol. This is obviously true also for multi-index tensors, since we can look at each index separately and go through our argument. All we need is the invariance of epsilon under SU2, which is the result of determinant 1, and the unitarity of U. The upper index objects can be expressed as linear combinations of lower indexed objects, as we see explicitly in the blue box, and are thus not independent components. This is why in lecture 23, where we have constructed higher angular momentum states out of spin half states, no distinction is made of upper or lower indices and the different ways which they transform under rotations. We need only one type of index for SU2. However, as we shall see, this feature is peculiar only to SU2. For the general SUN, both types of indices are required. For our next example, let's look at SU3, which will be relevant for the flavor symmetry of quarks. Again, these 3x3 matrices must have determinant of 1. Once more, the Leibniz formula is applicable. All indices now run from 1 to 3, thus the epsilon symbol must also possess 3 indices, which are totally anti-symmetric. This means the 3 indices in this expression, which are not summed over, must also be totally anti-symmetric. So we have once again an epsilon symbol. This has the same consequence as previously. The epsilon symbol is invariant under SU3 transformation. As we can see, the steps that led to the invariance of epsilon is quite general, as long as U has the determinant of 1. So the same result holds for SUN transformations for any n. Of course, for the case where the indices ran from 1 to n, the corresponding epsilon symbol must also have n indices. The invariance of the epsilon symbol under SUN is an important identity which shows up quite often in discussions about the tensor representations of symmetries. Going back to SU3, let's make use of the invariance equation. Notice that this equation also holds for the transpose of U, since UT is both unitary and has determinant 1. Now apply U star to the free index I1. Then using the unitarity of U, and we end up with this identity. As you can see, we can shift U to the other side of the equation, where it turns to U star and vice versa. This is just a simple consequence of unitarity. We have seen previously how to convert a lower index object into an upper index object using the epsilon symbol. This identity allows us to do the same here. Let's look at a tensor with 2 lower indices which are symmetric. This is an irreducible representation of SU3. Under SU3 transformation, we can define a tensor with an upper index in terms of this. This is how it transforms. Recall that a lower index transforms by U and an upper index by U star. So this becomes... Here's a chance to apply the identity above. Thus the upper index tensor we have defined really transforms like an upper index object. But here's the problem. The original 2-index tensor must be symmetric in order for it to be an irreducible representation. While the epsilon symbol is totally anti-symmetric in its indices, so this contraction must be 0. Thus an upper index tensor cannot be constructed this way. Therefore in this case, we would need both the upper and lower indices. They are independent degrees of freedom, unlike for the SU2. This would be the case for any SUN with n greater than 2, where the epsilon symbols all have more than 2 indices. Let's use the tensor coefficients to construct the SU3 multiplets of composite particles that are made out of quarks. Start with the simple example of particles composed of two quarks, one quark and one antiquark. This corresponds to a tensor with one upper and one lower index. Both the quark and antiquark come in three flavors. And because the tensor has only one upper and lower indices, it only needs to satisfy the traceless condition. In order to produce states that are in an irreducible representation of SU3. Given this constraint, the number of independent components equals the -1 takes care of the constraint, which gives 8 independent complex components. This is because psi ij is a complex tensor to begin with. Thus we have an octet. Here are the particles that correspond to this octet. They all have spin 0 and masses between 100 and 500 MeV. These particles consist of a kaon and anti-kaon doublet, a pion triplet, and a singlet of ether particle. They have hypercharges of 1, -1, and 0 respectively. This is an octet of particles each composed of two quarks. Roughly speaking, we could deduce that they are made up of two quarks by the magnitude of their masses. Because there is another octet, which is much heavier, where we could find the nucleons. This is an octet of spin-half particles with masses of around 1000 MeV. We have introduced this earlier. Recall that when we studied just the isospin doublet of the nucleons, we have concluded that the nucleons ought to be composed of three quarks. This is just so that the quarks' isospins sum up to the correct value of half. But how do we form a SU3 octet out of three quarks? We could still keep our earlier result if we let all the degrees of freedom of the three quark tensor coefficients be carried by the tensor psi ij. Here's how. Just make use of the invariance of epsilon. Pay close attention to how the indices are contracted. We can check that these tensor coefficients really transform like a tensor with three lower indices, just like three quarks. Under SU3, this is how the state psi transforms. This is the result of the transformation of the basis states. Rearranging the U's, we have we can rewrite this term by inserting a Kronecker delta. By unitarity, this delta can be broken down into U and U star. Here we can apply the invariance of epsilon. Check that the three indices are J', J2', and J3'. Changing the notation, moving the primes to unprime indices. Notice that this tensor in the red box is precisely the transformed tensor with one upper and lower index. Thus, the state we have constructed transforms effectively like a state in the SU3 octet. And this is a three-quark state as required. In this last example, we build a simple model which possesses the SU3 symmetry, which should flesh out some of the ideas that we have just developed. This is just a 3D harmonic oscillator from lecture 18. The field operator for a particle of flavor I, in this case, is AI dagger. They both act on the vacuum or ground state to give a single particle state. But in this model, there are no anti-particle state. AI acting on the ground state just gives 0. This equation serves to define the ground state. Here, the effect of AI is just to remove a particle of flavor I, while psi I dagger creates a different particle, which is the antiparticle. A typical eigenstate of this Hamiltonian comes from the actions of several ladder operators of different flavors on the ground state. Our convention is to label the states by the number of particles in each flavor. These states have eigenvalues given by, which we have worked out in lecture 18. We now verify that H has a unitary symmetry under the transformations of the ladder operators, like so. Again, repeated indices are summed over by the Einstein's convention. The transformed AI dagger AI summed over all flavors is thus given by, where we can use the unitarity of U. The second term in H associated with 3 halves is obviously invariant. Thus we have verified the SU3 symmetry of H. Next, we show that the commutators of the ladder operators are also invariant under this symmetry. This should already be apparent from the A-dagger combination on the left-hand side of this equation, as well as the delta symbol on the right-hand side. As for the rest of the commutators that are 0, this symmetry is even more obvious, since the linear transformation of 0 will remain 0. Let's see how these transformations might be implemented in Hilbert space. First, let's remind ourselves of some properties of the matrix U. We only have to examine the infinitesimal transformations, since finite transformations can be built from repeated applications of these. Theta ij is the infinitesimal deviation from the identity transformation delta. Recall that due to the unitarity of U, theta is actually I times a Hermitian matrix. This means theta is an anti-Hermitian matrix. U is completely specified by these parameters thetas. Let's promote this to an unitary operator in Hilbert space. Each of these parameters thetas will be associated with a Hilbert space operator x hat. These operators will implement the transformations of quantum states. The unitary condition means that this deviation from the identity operator is also an anti-Hermitian operator. What are the implications of this on the operators x hats? Let's take the Hermitian conjugate of this. Using the anti-Hermitian property of theta, we have. This is required to be the negative of the original operator in order for the term to be anti-Hermitian. Thus the Hermitian conjugate of xij needs to be xji, or equivalently, the switching of I and j is negated by the Hermitian conjugation. Now we can implement the transformations of the ladder operators using these unitary operators. The way that operators transform under symmetries in the Heisenberg's picture, as we have discussed in Lecture 4. Notice that we only need to work this out for the A's. After that, we automatically get the result we need for A daggers by taking the Hermitian conjugate. Again, we just need to consider an infinitesimal transformation. Substituting in U hat and the matrix U, we have a minus sign appears for U dagger, since this second term is anti-Hermitian. This gives us the conditions the generator's X hats have to satisfy. Using the commutators for the ladder operators, this equation will allow us to solve for the X's in terms of A's and A daggers. The key is to notice how a commutator appears on the left-hand side of this equation. This must be equal to the second term on the right-hand side. Now we compare terms on both sides of this equation. Let's see what this commutator should be in order to give the term on the right-hand side. Intuitively, the operator X ought to be of this form, which removes one particle and adds another. This is so that the symmetry operator U, when applied to the energy eigenstates, will not change their eigenvalues. The identity operator doesn't change the state, while X moves a particle of one flavor to another. Both operations do not change the total number of particles and, hence also the energy. Let's evaluate this commutator, which is easily done by applying the product rule of commutators that we have introduced way back in Lecture 1. Then use the commutation relations of the ladder operators, which gives minus delta I prime I. Compare this with the right-hand side. We realize that this minus sign is not needed. So let's define X with a minus sign. Thus we have derived the correct generators of unitary symmetry in terms of ladder operators. Here are the finite transformations. Which just comes from the repeated applications of the infinitesimals. Let's look at a simple example, which is just a multiplication of a phase to the ladder operators. This has the following implication for the Hilbert space generator. The operator X with identical indices is as follows. Where in the second line, we have used the commutators of ladder operators. This just results in a constant term, which commutes with all Hilbert space operators, and thus has no effect on them. So we can ignore this term. This gives, for the generator, We can write out the transformation of the ladder operators explicitly using the above results. Thus we see that the generator for a phase transformation is proportional to the Hamiltonian up to a constant term. This term is irrelevant as it just cancels with its complex conjugate in the transformation. Now let's locate the SU3 multiplets in this model. Recall that these are sets of states that cannot be moved out of the set by any SU3 transformation. It is easy to see that these are the degenerate energy subspaces where all the states within a subspace have the same energy. This is due to the fact that the symmetry generators cannot change the number of particles in a state. They just move the particles among the different flavors. U hat cannot change the particle number as we have already noted earlier, and thus also preserves the energy. As you can see, the degenerate subspace of fixed particle number corresponds to the SU3 multiplet. Denote this by curly N. U hat can only transform a state in N into another state in N. Recall that the particle number states are built up by multiple ladder operators of 3 flavors acting on the ground state. And all these A daggers commute. This makes their indices symmetric. And there are N indices corresponding to N particles. Under unitary transformation, this becomes, due to how the A daggers transform. If we want to keep to the convention of field transformation earlier, these U stars should be used instead. To correct this, we can define U hat like this. But this is only a matter of convention, because whether we have U or U star, both are unitary matrices. Now let's count the number of distinct states that have N indices. All these states have the same number of particles and energy. Furthermore, it is obvious that this fact cannot be changed by any unitary transformation since the number of indices doesn't change. Also notice that due to the symmetry of the indices, the way we count these states is exactly the same as how we count the number of independent components of a symmetric tensor. They have exactly the same number. And as we have shown earlier, the symmetric tensor corresponds to an irreducible representation of SU3 for 3 dimensions. Thus the degenerate subspace made up by these states is indeed an irreducible representation. Let's proceed with the counting. We have defined the number of ways n number of particles can be distributed into 3 types, 1, 2, or 3. We have to insert 2 partitions in these positions. For example, here's one way we could insert the partitions. The first section corresponds to N1, the second N2, and the third N3. Another example, if the 2 partitions are inserted into the same place, n2 equals to 0. The number of ways to distribute n balls into 3 boxes. The first partition can be inserted into n plus 1 positions, while the second partition can be inserted into n positions if we avoid the position of the first partition. We can take care of the cases where the two partitions are at the same position separately. We also need to multiply by half, since the ordering of the partitions doesn't matter. Now for the case where the two partitions are in the same positions. There are n plus 1 ways to place these partitions. Thus we have the number of ways of distributing n balls into 3 boxes, which is the same as the number of independent components in a symmetric tensor with indices that take 3 possible values. This in turn corresponds to the number of states in the degenerate subspace of n particles, which forms an irreducible representation of SU3. If you like this video, consider giving it a like and subscribe to this channel. And remember to press the notification bell so that you'll know when a new video is ready. See you next time, and thanks for watching.